Welcome to The Explainer. Today, we're embarking on a pretty incredible architectural adventure. We're going to dive right into this fascinating journey, from running a single local application all the way to orchestrating massive cloud-native cities. If you've ever wondered how modern tech giants run literally thousands of apps seamlessly without the whole shebang crashing down, well, you're in exactly the right place. Here's our roadmap for today. We'll be covering monoliths to microservices, the Docker blueprint, connections, data, and security. Then we'll enter Kubernetes orchestration and wrap up with scaling real-world applications. All right, let's hit section 1, monoliths to microservices, breaking down the behemoth. So historically, software was built as a monolith. Imagine a massive, complex machine where every single gear is just welded together. If one gear breaks or even just needs a minor upgrade, you have to shut down and disassemble the entire machine. That means prolonged, painful release cycles. Microservices totally change the game. We break that massive machine down into much smaller, independent components. Say you want to update the payment service of your app. You just update that one specific piece without touching the rest. It's modular, it's fast, and it is absolutely the foundation of cloud-native computing. Moving right along to section 2, the Docker blueprint, building the foundation. Enter Docker. To really wrap your head around how Docker works, it's kind of like a company building prefabricated houses. The Docker file is your blueprint, literally just a text file with instructions. Then the Docker image is the specific house model you pick out of a catalog. And finally, the Docker container is the constructed house you actually live in, running out there in the real world. Because we have that ultra-reliable blueprint, we can build that exact same house 1,000 times over, and it'll be identical every single time. Taking a quick look at the command line, we can see exactly how this builds. You just use these commands to turn that blueprint into a reality. First, you run docker build dot to execute the instructions in your Docker file, which bakes them into a static image. Once that image is ready to go, you simply use docker run to spin up a live running container. It's incredibly elegant. But beneath the surface, Docker is doing something highly intelligent to make this whole process blazingly fast. And that intelligence? It's all about layers. Every command in your Docker file creates a brand new layer, which is essentially just a snapshot of a file system change. So the really crucial takeaway here is that Docker uses these cached layers to speed things up, which is exactly why we always put the least changing instructions at the top of our blueprint. If you're installing standard software packages, do that first. Those layers get cached. Then, copy your frequently changing source code at the bottom. This makes sure you aren't rebuilding the entire image from scratch every single time you fix a minor typo in your code. Let's jump to section 3, connections, data, and security, the infrastructure. Okay, let's talk security. Containers naturally provide inherent isolation from the host operating system, which is fantastic. But applying a few punchy security best practices ensures attackers can't easily break out into the host machine. You always want to pull your base images from trusted registries. Keep your software updated. Keep your images as minimal as possible because, remember, there is no safer piece of software than the one you never installed. And crucially, don't run your applications as the root user. Just switch to a user with fewer permissions right before your container executes its main process. Next up is data. Because containers are ephemeral, meaning they can be destroyed and recreated literally at any time, we have to use bind mounts or higher performance persistent volumes to ensure our data isn't wiped out when a container stops. Bind mounts act kind of like a direct window to a folder on your host machine. Docker volumes, on the other hand, are managed entirely by Docker itself. They offer much better performance and are absolutely the recommended way to share databases or log files safely between multiple containers without messing with the host's specific file paths. Finally, we've got to build the roads. To allow our isolated containers to actually talk to one another, Docker uses networking drivers, like the bridge driver. This essentially creates a virtual local area network right inside your machine. Containers on the same bridge network can communicate securely, and they can reach out to the internet, but they remain wonderfully isolated from external threats. Now, Docker is absolutely amazing for running, say, a few dozen containers. But this brings us to a massive scaling wall. Doing all of this manually for 1,000 containers? Yeah, that's practically impossible. Imagine trying to manually restart 500 containers if a server crashes, or hand configuring the network routing for all of them. No way. To solve this, we move to section 4. Enter Kubernetes orchestration, the city planner. Kubernetes, often abbreviated as K8, interacts with a container engine like Docker to orchestrate your entire fleet effortlessly. If Docker is the company building the prefabricated houses, Kubernetes is the city planner that decides exactly where those houses go, builds the highways, makes sure the water is running, and automatically rebuilds a house if it gets leveled by a tornado. It really is the de facto operating system for the cloud. There's a major conceptual shift here, though. In Kubernetes, we actually don't deploy raw containers. Instead, we deploy pods, which are highly ephemeral and can be recreated at a moment's notice. A pod acts as a wrapper around one or more containers that need to share the exact same network IP and local storage. They are born together, they die together, and they scale together. So how does Kubernetes actually know where to put these pods? The control plane acts as the city planner's brain, ensuring every single pod finds an appropriate node, which is really just a worker machine or server, to live on. If you tell Kubernetes you want 10 replicas of your web server pod, the control plane looks at all your available nodes, checks their CPU and memory, and smartly distributes those pods across the cluster for maximum efficiency. If a node catches fire, the control plane instantly notices and reschedules those lost pods onto healthy nodes. It's completely self-healing. But here's the catch. If pods are constantly dying and being recreated on different servers, their IP addresses are constantly changing. Because of this, services step in to provide a stable, permanent address and distribute network traffic evenly. A service basically sits right in front of your pods. When a user requests your app, they hit the service's permanent IP, and the service acts as a load balancer, seamlessly routing that traffic to a healthy, currently running pod in the background. And that brings us to Section 5, Scaling Real-World Applications, Pipelines, and MLOps. First things first, we need to handle our data safely. By strictly separating storage from compute, Kubernetes uses this three-part structure to ensure your databases and pipelines literally never lose crucial data. When your application needs storage, it submits a persistent volume claim, essentially asking the cluster, hey, I need 50 gigs of fast storage. The storage class dynamically provisions that exact requirement on the fly, creating a persistent volume. Even if the pod computing the data is completely destroyed, that persistent volume remains perfectly intact and will instantly reconnect when a new pod spins up. Let's look at how we handle ETL data pipelines at scale. In modern data engineering, we extract data from various sources, transform it into meaningful formats, and load it into databases. And Kubernetes is an absolute dream for this process. Because we've separated compute and storage, we can actually scale them independently. So if your transformation step is dragging its feet, you simply ask Kubernetes to scale your deployment up from 5 pods to 10 pods instantly. You get double the processing power exactly when you need it to chew through massive data sets, and then you can just scale it right back down to save money when the job is done. And this scalable logic, it applies directly to artificial intelligence as well. We can seamlessly map machine learning operations onto Kubernetes, using frameworks like Kubeflow to constantly improve and retrain AI models right in production. Data scientists can run isolated experiments in their own dedicated pods with attached storage. And with tools like Kubeflow, they can interact directly with the Kubernetes API using Python. That means they can deploy incredibly complex AI workflows without ever having to become a command line expert. Well, we've journeyed from fragile monoliths to resilient, automated, cloud-native cities. As you look at the infrastructure you manage today, ask yourself, how can you leverage these blueprints and city planners to scale effortlessly into the future? Whether you're running a simple website, a massive data pipeline, or cutting-edge AI models, container orchestration is the foundation you need. Thanks for joining me on this explainer, and I really hope this gives you the clarity you need to go out there and start building.